So now we are going to discuss the last topic of chapter 7, point estimation. Which is loss function, optimality, and statistical decision theory. So before we talk about loss function, optimality, so remember previously we mainly used the mean squared error as our matrix to evaluate the performance of a point estimator. Okay, so the MSE can be written as the sum of the square of bias plus the variance. And previously, we mainly talk about the performance of unbiased estimator, so which means the bias is 0. And we look at those unbiased estimator with the smallest variance, or we call the best unbiased estimator, or UNVOE. Okay, so and recall that we have discussed the two methods to find the UNVOE. So the first one is the based on the CR lower bound, CRLB. Okay, and the second method is based on the basically conditioning on the complete sufficient statistic. So which is the Lemon-Shaffey theorem. Okay, so based on the complete sufficient statistic. Okay, so actually the MSE is a special case of a function which is called the loss function, which is a general way to evaluate the performance of a point estimator. Okay, so which we are going to discuss now. So first, let's look at one example of loss function. Okay, so let's consider the point estimation problem. Okay, so we want to use theta hat to estimate the parameter theta. This problem can be viewed as we want to make some decision about the parameter theta. Okay, and then what we used is the MSE, so defined as the expectation of the square of the difference between the point estimator and the true value of the parameter. Okay, so now we can view the MSE as a loss function, or we say the cost associated with our decision. Okay, so then we have two situations. So if our point estimator theta hat is exactly equal to theta, so that means we make a correct decision. So then our cost is 0. So that means the MSE is 0. Okay. Another situation is if we make a mistake, so that is our point estimator theta hat does not equal to theta, the true value of theta. So then we make a mistake, and then we will get the MSE greater than 0. So in other words, our loss is greater than 0. So in this way, we can view the MSE as some loss or cost associated with our decision about making a point estimation of theta. Okay, so next let's come to the definition of what is a decision. So the definition of a decision. So after the data X are observed, where the X follows some probability distribution F, so a decision, or in other words, a decision action or decision rule A, so regarding the parameter theta is made. Okay, and the set of all allowable decisions is called the action space, so denoted by A. Okay, so now let's come back to our point estimation problem. So in this point estimation problem, so the decision A is just to find a point estimator of theta. Okay, so here the A in the point estimation problem is just the theta hat, a point estimator of the parameter theta. Okay, and the action space. So the action space is all the allowable decisions. So in this point estimator problem, so that is all the possible values we can guess to find the point estimator. So here is just equals to the parameter space big theta. Okay, so the parameter space. So this is the definition of a decision and the action space. So in point estimation problem, the decision is just the point estimator of theta, and the action space is just the parameter space. Okay, so the next definition is loss function. Okay, so in point estimation problems, the loss function is a non-negative function that generally increases as the distance between the action A and theta increases, so denoted as L theta A. Okay, so in other words, the loss function is a non-negative and also the increasing function as the distance between our point estimator A and theta. Okay, so now let's look at some examples of loss function to further understand the definition of loss function. Okay, so here we write the L theta hat as a loss function of theta and the theta hat. Okay, so here the theta hat is a point estimator of the parameter theta. Okay, so one of the widely used loss function is called squared loss. Okay, so here the squared loss is just the square of the difference between theta hat and theta. Okay, so like in the mean squared error MSE, so that is we take the expectation of the squared loss function, so which is the average of squared loss. Okay, so on next page we have another example. So the next example is of loss function is called the absolute error loss. Okay, so which is defined as the absolute value of the difference between theta hat and theta. Okay, so if we want to compare those two loss functions, the squared error loss and the absolute error loss, so we can draw a plot here. Okay, so say at the middle point is the true value of theta. Okay, and then on the x-axis is the value of our point estimator theta hat. Okay, so then we have those are the two the shapes corresponding to the squared error loss and the absolute error loss. Okay, so what we can see is when the difference between the point estimator theta hat and theta grows, so then the squared error loss will have larger values. The squared error loss will have larger values than the absolute error loss. So we can see this. Okay, so that means the squared error loss gives more penalty on large discrepancies between theta and theta hat, so which is shown in this plot. Okay, and here for the absolute error loss, so it gives more penalty on the small discrepancies between theta and theta hat, comparing with the squared error loss. So this can be seen from this plot. Okay. Okay, and then we have a lot of different versions of loss functions. Okay, so for example, we can one example is the following combination of the loss functions. Okay, so it's so this loss function means when the theta hat is less than theta, so the loss function is equals to the squared error loss, this part, when theta hat is less than theta. But when theta hat is greater than theta, okay, so then this loss function becomes 10 multiply the squared error loss. Okay, so this type of loss function will penalize overestimation much more than underestimation. Okay, so that means when theta hat is greater than theta, we will have more penalty. Okay, because we have a value of 10 here. Okay, so there are many different types and forms of loss functions, and then each of them will have different properties. Okay. So the next definition is called the risk function. Okay, so here the definition of risk function is so the quantity of a decision rule, okay, we write as delta, so is quantified by its risk function. Okay, so which is defined as the expectation of the loss function. Okay, so risk function is the expectation of the loss function. Okay, and in other words, that is given a parameter value theta, the risk function is the average loss that will be incurred if the estimator delta x is used. Okay, so here delta x is just the notation used in the decision theory. Okay, so here in our point estimating problem, so that is just the theta hat we used. We want to find a point estimator. Okay, and the risk is the average of the loss function. So in other words, the average loss when we use the estimator delta. Okay, so when we talk about the loss function optimality, the loss function and the risk function, so those are all the concepts in the field in statistics, which is called the statistical decision theory. Okay, so in statistical decision theory analysis, the goal is to find an estimator that minimizes the risk. So in other words, we want to find an estimator that minimizes the average loss, the risk. Okay. So as what we have seen, okay, so this goal is more comprehensive than only focusing on the unbiased estimator we discussed before. Okay, so in the sense that we are considering both the bias and the variance are in the risk. Okay, and we consider both bias and variance simultaneously. So we want to find a estimator that minimizes the risk, the average loss, and the loss have incorporated both the bias and the variance. Okay, for example, the MSE, we will see soon. So MSE is actually the risk of the squared loss function, the risk under the squared loss function. So it considers both the bias and the variance. Okay. So I would say here the statistical decision theory, you will learn more in next year in the base course. So here in this section, we will discuss the basic concepts and definitions. Okay, so now let's look at one example about the how to find the best estimator under the statistical decision theory analysis. Okay, so now let's look at this example. So our data X are from the normal distribution. So now let's consider estimating the variance sigma square using the squared loss function. Okay, so that means we want to estimate the variance sigma square under the squared error loss function. Okay, and then now let's consider all the estimators of this form. So of the form B multiply S square. So B is a can be any non-negative constant. That is the value we want to find. And the S square is the sample variance. Okay, so we want to find the best estimator of this form, B multiply S square. We want to find the best estimator of this form for the population variance sigma square under the squared error loss. Okay, so in other words, we want to find the estimator of this form that minimize the risk, okay, the risk under the squared error loss. Okay, so to solve this problem, we first need to write out the form of the risk under the squared error loss. Okay, so here our loss function L is the squared error loss. Okay, so which is the square of the difference between theta hat and theta. Okay, so now let's evaluate the risk under the squared error loss. Okay, so which is here. So that is the average of the squared error loss function. So which is here. Okay, so we can immediately see, okay, this risk is the expectation of the squared error. So which is exactly the mean squared error is the MSE. Okay, so which can be written as the variance of the point estimator plus the square of the bias of the point estimator. Okay, so here we just change about the notation, we just change the theta hat to the delta x following the notation in the statistical decision theory. Okay, usually we use the delta as a decision rule or decision action in the decision theory analysis. But remember, this is just here the delta is just the same as the theta hat we used before, so which is a point estimator. Okay, so here again, I want to emphasize this. So the risk under the squared error loss just equals to the MSE. So which is can be written as the variance plus the square of bias. Okay, so now let's evaluate this MSE or the risk. Okay, so now we plug in the form of the point estimator. Okay, so which is B multiply S square. Okay, so we plug in the variance and also the bias here. Okay, so and we need to do some algebra. So here for the variance, we take out the square of the constant B. Okay, and then here this is the calculation for the expectation. Okay, so from here to here, we just use the one result in the previous example. Okay, so in this example, we have shown the the variance of S squared, the sample variance equals to this for normal distribution. Okay, so then which is we plug in the value here. Okay, we got this. Okay, and then here the excitation of S squared is so S squared is unbiased, so which equals to sigma square. Okay, so then we have the constant is b minus 1 square multiply the square of sigma square, so which is cubic of sigma, so which is here. Okay, so now let's briefly rearrange the terms. So we have the cubic of sigma multiply those terms contains the constant b here. Okay, so then we can rearrange the terms, and we got this. Okay, so based on the form here, so we want to find the value of b that minimize this part. Okay, so this is a quadratic form of b. Okay, so to find b, the value b minimize this quadratic polynomial. So we can take the first order derivative of this and set it to 0, and then solve for b. Okay, and then we can alternatively we can also complete the square for b. Okay, so which gives us the value of b minimize this quadratic polynomial is this one, n minus 1 divided by n plus 1. Okay, so this is the value of b we want to find, so which minimize the I minus e, or the risk under the squared error loss function. Okay. Okay, so to summarize the result, okay, so the optimal estimator minimize the I minus e, or we call the optimal I minus e estimator. So we use the S square tilde to denote this estimator. So which is the b, the value of b. What we found here is this one multiply the S square. Okay, so which gives us this point estimator. Okay, and if we plug in the value of b, so we can easily get the value of I minus e under for this point estimator, so which is here. Okay, and in this figure, in this plot, we just want to compare this optimal I minus e estimator with the other estimators we have seen before. Okay, so remember previously in the last lecture, we also find the UMVUE. So that is the best unbiased estimator of sigma square. So remember this is unbiased estimator. Okay, so which is exactly S square. So the sample variance. So the sample variance is the UMVUE of sigma square. Okay, so this one gives the I minus e of this value. Okay, and then previously we also found the MLE of sigma square. Okay, so which is just up to a constant comparing with S square. And this point estimator gave us the I minus e of this value. Okay, so if we plot those three, the I minus e's with those three point estimators, we will get this those three lines. Okay, so here if we compare the risk, so which is the average loss of those three point estimators, so we can see the optimal I minus e estimator always has the smallest risk. Okay, so in other words, here for this optimal I minus e estimator, it minimized the MSE, so which combined both the bias and the variance. Okay, so this is about this example. Okay, so the next part, we are going to discuss about the Bayesian approach to the loss function optimality. Okay, so what we just discussed is the basic definition and concepts of loss function optimality under the frequentist framework. Okay, so the second part is about the loss function optimality under the Bayesian framework. Okay, so it's a little bit complicated than the frequentist framework because the prior distribution is involved in Bayes framework. Okay, so first let's look at several definitions. So what we are going to look at for the risk and the loss function optimality under the Bayes framework. Okay, so the first definition is called the Bayes risk. Okay, so remember the under the frequentist framework we just discussed. So the risk is just the average of the loss function, the average loss. Okay, so here the Bayes risk of a decision rule. So here, remember the decision rule here is just a point estimator. Okay, but we use notation delta. Okay, so the Bayes risk of a decision rule delta is defined as it is still an average risk. Okay, is the average risk across all the values of theta given a prior distribution pi theta. Okay, so in other words, what is added in the Bayes risk is now we still consider the Bayes risk as the average risk, but now we have a prior distribution pi theta. So the Bayes risk is defined as the average risk across all the values of theta under a prior distribution pi theta. Okay, so if we write in formula, so that is the integration of the risk multiply the prior distribution of theta. So which means the average risk across all the values of theta given a prior distribution pi. Okay, so in other words, in addition to the frequentist risk we just discussed, okay, so the Bayes risk has one more component of the prior distribution. So we need to integrate the risk over all the values of theta under the prior distribution. So this is the definition of Bayes risk. Okay, so next definition is called the Bayes rule estimator. Okay, so the Bayes rule estimator is the one that results in the smallest value of the Bayes risk. Okay, so the Bayes risk, the definition of Bayes risk is we just discussed. So is this. So the estimator gives us the smallest value of the Bayes risk is called the Bayes rule estimator. Or it is alternative term is called the Bayes action estimator. Or sometimes you can see it is simply called the Bayes rule. Okay. So this is called the Bayes rule estimator with respect to a prior pi theta. Okay, so which is denoted by delta pi. Okay, so in the Bayes decision theory analysis, we usually want to find this Bayes rule estimator. So in other words, we want to find the point estimator that minimize this base risk, so which is the integration of the risk across all the values of theta under the prior distribution pi. We want to minimize this base risk. But the problem is usually this base risk, if written in this integration form, it is not easy to minimize. So then we want to write this base risk in an alternative form, which is easier to work on. Okay, so then we will have the next definition, so which is called the posterior expected loss. Okay, so now we want to try to write the base risk in an alternative form. Okay, so now let's work on this. Okay, so here this is the definition of the base risk. Okay, so we write here, so which is the risk over all the values of theta given the prior distribution pi. Okay, so now let's write out the definition of this risk. Okay, so remember the risk is the average loss, so which is the expectation of L. Okay, expectation of L multiply the prior distribution and integrate over the whole parameter space theta. Okay, and now let's write out this expectation. Okay, so here this expectation of L equals to this. So that is the loss function. Okay, multiply the PDF of X. So this is the definition of this expectation. Okay, so which is and integrate out over the sample space X. So this is the definition of this expectation, this part. Okay, this is the definition of this expectation. Okay, and then we have the prior distribution of theta. Okay, so now let's remove the brackets here. Okay, and then we have those three terms. The first one is the loss function. Okay, second term is the sampling distribution or PDF of X. Okay, and then multiply the prior distribution. So now we are going to use the Bayes rule here. So remember we have this. Okay, so sampling distribution multiply the prior distribution, so equals to the joint distribution of the random sample X and the parameter value theta. Okay, so which can be written as this is the posterior distribution of theta given the random sample X multiply the marginal distribution of the random sample X. This is based on the Bayes rule, and we have discussed this in the previous lecture. Okay, so now we are going to use this. So this is the sampling distribution multiplied prior. So we can write this as the posterior distribution of theta given X multiply the marginal distribution of the random sample X, so which is here. Okay, so now we put every term, each terms containing the parameter value theta together. Okay, so now we have the loss function. Okay, and the posterior distribution of theta given X. Okay, and then we put the integration of theta together here. Okay, and then we have this form. We write the base risk in this form. So inside the brackets, we have all the terms containing the theta. Okay, so here we once if we look at this form now, okay, so here we only need to minimize, we only need to find the delta that minimize the term inside these brackets. Okay, because only this term contains the parameter value theta. Okay, and then outside these brackets, those are the the margin distribution of x. Those are the integration with respect to x, so which does not depend on theta. Okay, so then we can ignore those terms does not depend on theta. So in other words, we only need to find the delta that minimize this integration inside these brackets. Okay, so this quantity inside the brackets is called the posterior expected loss of a decision rule delta. Okay, so here, remember the decision rule, this is just a general form, a general term for the statistical decision theory. So in point estimator, a decision rule delta is just a point estimator. Okay, so remember this notation. So in other words, to find a Bayes rule estimator that minimize the Bayes risk is equivalent to find a point estimator that minimize this posterior expected loss, so which is here. Okay, so this posterior expected loss is the expectation of the loss function. You see here, this is the loss function. This is the expectation of this loss function with respect to the posterior distribution pi of theta given x. Okay, so again, let's look at this. This is the loss function, the expectation of the loss function under the posterior distribution. So you can see that, right? Okay, so then an alternative and equivalent definition of the Bayes rule estimator, okay, is the estimator that minimizes this posterior expected loss. So this is what I just explained. Okay, so we only need to look at those the delta that minimize those terms contains theta, so which is this posterior expected loss inside these brackets. Okay, so this is about the Bayes rule estimator. So we want to find the Bayes rule estimator that minimizes the Bayes risk. Okay, so which is equivalently minimize the posterior expected loss, so which is here. Okay, so now let's look at some real examples about how to find this Bayes rule estimator. Okay, so we have the example here. Okay, so now let's consider about finding a point estimator of the parameter theta. Okay, so remember that we want to find the Bayes rule estimator that minimizes this posterior expected loss. So the form of this posterior expected loss will depend on the form of this loss function. Okay, so now we are going to look at two examples. Okay, so the first example is our loss function. The form of our loss function is the squared error loss. Okay, so then our posterior expected loss is this. Okay, the squared error loss multiplied the posterior distribution. Okay, so here we can write this integration as the as the expectation here. Okay, so which is the expectation of the squared error loss under the posterior distribution. So that's the meaning of this subscript. Okay, so which means the expectation is taken with respect to the posterior distribution. Okay, so here we want to show the Bayes rule estimator that minimizes this posterior expected loss is actually the mean of the posterior distribution. Okay, we want to show this soon. We want to show this result. Okay, so that is the Bayes rule estimator with the squared error loss is the posterior mean. So the mean of the posterior distribution pi theta given x. Okay, so the second example is if we look at the Bayes rule estimator, under the absolute error loss. Okay, so what is the Bayes rule estimator under the absolute error loss? Okay, so under the absolute error loss, the posterior expected loss is given in this form. So this is the absolute error loss multiply the posterior distribution and integrate over all the values of theta. So which is the expectation of the absolute error loss under the posterior distribution pi theta given x. Okay, so we want to show the Bayes rule estimator minimize this expectation is actually the median of the posterior distribution. Okay, so now let's look at how to show these two results. Okay, so the first result is under the squared error loss, the Bayes rule estimator that minimizes the posterior expected loss is the mean of the posterior distribution. We want to show this result. Okay, so remember in the last semester, we have shown this result. Okay, so we want to find a quantity b that minimizes the expectation of x minus b squared. Okay, and the x follows some probability distribution. Okay, so we already shown the b minimize this expectation is the expectation of x. Okay, so in other words, the expected value of x will minimize this expectation. Okay, so I'm not going to repeat this now. Okay, so we can, if you forgot this result, you can go back to this example we have discussed before. Okay, so using this result, so now let's look at the form of the posterior expected loss under the squared error loss, so which is here. Okay, so that is actually takes exactly the same form as the previous example, right? Okay, so use this result, then we can immediately see, okay, the point estimator delta that minimize this posterior expected loss is the mean of the posterior distribution. So in other words, so that is the Bayes rule estimator equals to the posterior mean of theta. Okay, so that is about the first example. And for the second example, okay, so first we still need to prove a result regarding the median. So this is given in the exercise of 2.18 in the textbook. Okay, so about the median. result about the median. So we want to show the result, prove the result here. Okay, so the result is this. So if x is a continuous variable, so then if we want to find the value a that minimizes this expectation, so that is the expectation of the absolute value of x minus a. We want to find a value a that minimizes this expectation. So the value a is the median of x. Okay, and then how can we prove this result? Okay, so now let's use fx to denote the PDF of x. Okay, so then we can write this expectation based on the definition of expectation. We can write this as the integration. Okay, this absolute value multiply the PDF of x and integrate out the sample space of x. This is the definition of the expectation. Okay, and then we write this integration as the sum of two parts. Okay, so for the first part, if x is less than a, so then that is the integration, the range of the integration is from minus infinity to a. Okay, and then this absolute value will be minus of x minus a. So this is the first part. So for the second part, we evaluate this integration from a to positive infinity. Okay, so then we have this absolute value as x minus a, which is here. Okay, so now we are going to take the first order derivative of this expectation. Okay, so we can use the Leibniz's rule to find the first order derivative of this integration, the sum of those two integrations. Okay, so after we take the first order derivative with respect to a, so for the first term, we will have this here. Okay, and the second term, we will have this part here. Okay, so I'm going to just omit some calculations and ask you guys to verify this. Okay, so we will have those two terms. Okay, so remember we want to find the value a that minimizes this expectation. So we want to set this first order derivative equals to 0. So then we will have this equality. Okay, so that is the integration of the PDF fx from minus infinity to a will be equals to the integration of fx from a to positive infinity. Okay, so if we look at the definition, okay, the definition of the median. So the definition of the median is it is the value in the sample space that gave the same probability of the integration from minus to m and from m to positive infinity. So this is the definition of the median. Each of those two integrations or the probabilities takes the same value as 1/2. Okay, so this is the definition of the median. Okay, so then we can see, because we have this equality, we can see this exactly that follows the definition of the median. So then a is exactly the median. Okay, to be more accurate, we also need to check the second order derivative to confirm this expectation takes the minimum value at the median. Okay, so we need to check the second order derivative to make sure the second order derivative is greater than 0. Okay, So then we can say this median will give us the minimum value of this expectation. Okay, so by using this result, now let's look at the form of the posterior expected loss under the absolute error loss. Okay, so this is exactly the form of the expectation of an absolute error loss. Okay, so then we want to find the Bayes rule estimator delta that minimize this expectation of absolute error loss. So which use the result we just discussed, we can immediately see, okay, so this Bayes rule estimator minimize this expectation will be the median of the posterior distribution. Okay, so the median of the posterior distribution. Okay, so that's about this example. Okay, so to summarize, under the squared error loss, so the Bayes rule estimator will be the mean of the posterior distribution. And under the absolute error loss, the Bayes rule estimator will be the median of the posterior distribution. Okay, we have shown these two results. Okay, so now let's look at another two examples using these results. So the first one is the normal Bayes rule estimator. So here our data is from the normal distribution. And then we suppose the prior distribution on theta is also a normal distribution. So here we assume the sigma square and the two hyperparameters mu and tau are known. So we want to find the Bayes rule estimator of theta under the squared error loss and also under the absolute error loss, respectively. Okay, so to solve this problem, first we recall in our previous lectures and also the homework problem, we have found the posterior distribution of theta given x is also a normal distribution with this mean, with this posterior mean. Okay, so that is a linear combination of the sample mean and the prior mean. Okay, and then with this variance. So those are the results we already did before. Okay, so now I'm going to apply the results we just discussed. Okay, in the previous example. So under the squared error loss, so we said the Bayes rule estimator will be the posterior mean. Okay, so in this normal example, so that is exactly equals the posterior mean, so which is here. Okay, and then the second question is the Bayes rule estimator under the absolute error loss. Okay, so use the result in the previous example. So that is the posterior median, right? The median of the posterior distribution. So here in this normal example, because the normal distribution is symmetric, so the mean is the same as the median. Okay, so then in this example, under the absolute error loss, so the Bayes rule estimator will be the posterior median, so which is the same as the posterior mean, so which is here. Okay, so next example is about the binomial Bayes rule estimator. So here our observations X are from the Bernoulli distribution. Okay, and the Bernoulli probability P is the unknown parameter. Okay, so then the sum of the IID Bernoulli is the binomial distribution. So we assume the prior distribution on the probability P, the parameter P is a beta distribution with parameters alpha and beta. And here both alpha and beta are known. Okay, so given that Y as our observed data, let's find the Bayes rule estimator of P under the squared error loss and the absolute error loss. Okay, so first, still use the result in the previous example. So we know this is the beta binomial conjugate family, right? So the posterior distribution of P is a beta distribution. Okay, so we have derived this before. Okay, so now we are going to use the results from the previous example. So under the squared error loss, so what is the Bayes rule estimator? So that is the posterior mean, right? Okay, so which is the mean of this posterior beta distribution? So which is here. This is the mean of this beta distribution. Okay, so the second question is under the absolute error loss. So remember that the Bayes rule estimator will be the posterior median, the median of this beta distribution. Okay, so here we cannot solve the median of this beta distribution explicitly. So there is no analytical form for the posterior median. But we can express this using the formula here. Okay, so that means the integration of from 0 to the median value. This is the PDF of this beta distribution. Okay, so this integration takes the value of 1/2. Okay, so this can be solved numerically like in R or MATLAB using those software tools. We can easily solve this integration. Okay, so then this is the posterior median is the Bayes rule estimator under the absolute error loss. Okay, and in the last page, the last table, we just gave those Bayes rule estimators under both the squared error loss, so which is here, squared error loss, the Bayes rule estimator under the squared error loss, and the Bayes rule estimator under the absolute error loss. Okay, and then we assume the prior distribution is the uniform distribution, and the number of observation is 10. And here are the values of Y. Okay, for each specific values of Y, so this table lists the maximum likelihood estimator. So which is the frequentist estimator, point estimator we learned before, the MLE. Okay, and then also the two Bayes rule estimators we just discussed here. So now this table gives us the specific values for each different values of Y. Okay, so what we can see is the general trend is when the value of Y increases, it has more weights. The sample will have more weights in the estimator. Okay, so then both all three types of estimators grows with the value of Y. Okay, but another interesting thing is if we look at the two extreme values of Y equals to 10, equals to 0 and 10. Okay, so the MLE will be goes to the two extreme values of 0 and 1. But the Bayes rule estimator will never give the two boundary values of 10 of 0 and 1. Okay, remember here the P is the parameter, the probability parameter, so which is in the range between 0 and 1. Okay, the Bayes rule estimator will never go to the two boundary values. So that is because we have the weight of the prior distribution. Okay, the prior distribution will play a role in the Bayes rule estimator. Okay, so that is all about this part, the loss function optimality. Okay, so what we need to learn, we need to know is first the basic definitions, okay, about the what is called a decision. Okay, those basic concepts, and what is the loss function. Okay, so this is a very important concept. Okay, and then under the different form of loss function, so what is the risk function and how to evaluate the risk function? So those are the basic concepts of statistical decision theory. Okay, and the second part we talk about the several concepts of the loss function optimality under the Bayesian framework. Okay, so like what is the Bayes risk and what is the Bayes rule estimator? Okay, and what is the posterior expected loss? So this is just an alternative form for the Bayes risk. Okay, and then specifically we discussed the two specific type of Bayes rule estimators and under two different form of loss functions. So under the squared error loss, the Bayes rule estimator will be the posterior mean. And under the absolute error loss, the Bayes rule estimator will be the median of the posterior distribution. Okay, so that's all about this part. And next lecture we will discuss the new chapter. Okay, see you.